Hi. There has been a lot of recent research focus in on-device deep learning for audio recognition tasks like keyword spotting, urban sound classification, etc. Federated learning is an effective way of training across a federation of multiple decentralized devices along with a centralized model. Unlike the conventional ways of sharing data, there is transfer of model weights and model updates. This strives towards privacy preservation of user data with minimal latency and more personalization as well. Apart from the challenges like privacy concerns, communication overheads, and system heterogeneities, we address two other important challenges. The first is identifying and distinguishing between the new classes across devices, since sensitive data transfer is not encouraged in federated learning settings. The next is addressing statistical heterogeneities and allowing end users to characterize their own label distributions and model architectures. To solve the problem of not exposing local sensitive data, we construct anonymized data impressions in a zero-shot manner, motivated from the zero-shot knowledge distillation paper. To create this, the class similarity matrix is first created, which contains important information on how similar the classes are to each other, and is obtained by considering the weights of the model/layers. The softmax values are then sampled from the distillate distribution. Further, to synthesize the data impressions, we minimize the cross-entropy loss when modeled from random input data. The overall architecture of the proposed framework is shown here. The softmax values are first sampled for newly reported classes in the local models and are sent to the global user, where the corresponding data impressions are generated, followed by unsupervised clustering to distinguish between the new classes. This happens across different iterations within the typical federated learning workflow. There are three typical steps in our proposed framework. Initially, we build the model for the local user. The local update step is used to obtain local model scores. When new classes are reported, train the new model together with public data and new data, and use weights of the last layers for sampling softmax values. Finally, the global update step is used to perform weighted average of scores across all users. When new classes are reported, we create average data impressions as discussed, followed by k-meroids clustering, and the corresponding data impressions and labels are then updated back to the public data. In our experiments, we use two datasets, Google speech commands for keyword spotting and urban sound 8K for urban sound classification. Initially, we split the data into 3 different local users and used 10 classes with 2 new classes each for both datasets. We first observed the results using just 3 users and 10 federated learning iterations, and we observed the average accuracies of all global updates are higher than the respective local updates for both datasets. To truly showcase near real-time statistical heterogeneities, we also changed the models and label distributions with new classes across and within various federated learning iterations. We also observed the results for a more practical realistic scenario with 10 users and 30 federated learning iterations with both new classes and statistical heterogeneities. We can observe the local and global update accuracies per user in the graphs here and a solid increase for both datasets. After creating anonymized data impressions on newly reported classes, unsupervised clustering with k-meroids algorithm is performed. PCA visualizations are seen here to distinguish between them. We can also observe the Raspberry Pi 2 computation times and model sizes for federated learning epochs and inference with our proposed framework. Thank you.